Let's do an example now with a moving proton. We've got part A and B here, and the difference between parts A and B is the direction of the velocity. We want to find the magnetic force. We know that's equal to QV cross B, and we've got two ways. We can do the cross product in the equation, or we can do magnitude and direction. Let's do the cross product for A, magnitude and direction for B. In both cases, Q stands for the charge on a proton, which is plus the fundamental charge, or positive 1.6 times 10 to the minus 19 coulombs. Let's get started with part A. We'll write down the equation. FB equals our charge. I'm just going to write that as E times V crossed with B. If you look at our velocity, we see that it does have components. It's got an X component that points to the right, Vx. It's got a Z component that points up, Vz, and the angle of our vector is 45 degrees. The X component is adjacent to the angle, so it's V times cosine 45. You might remember that cosine 45 is root 2 over 2. And if you wish at this point, you could put in 1 times 10 to the 7 times root 2 over 2 to get a number here for your velocity. I'm not going to do that just yet because I just don't want to have to write down too many numbers. Vz is V times sine 45. And sine 45 is also root 2 over 2. So when we write our velocity is a vector, we've got our x component, which is v times root 2 over 2. That's in the x direction. And that's plus v times root 2 over 2. That's the z component, so that's got a k hat for k direction. That's going to be crossed with our magnetic field. The magnetic field is 0.5 teslas in the I direction or to the right. Okay, let's multiply out the distributive property here. We've got E times V times root 2 over 2 times 0.5 teslas. There's all of our constants. Then we'll do the vector part, I cross I. Then we have the second part, E times V times root 2 over 2 times 0.5 teslas times K cross I. This first term is all 0 because we know that the cross product of parallel vectors equals 0. For this one, what is K cross I? Well, you might do the triangle or you might just remember. We see that K cross I is equal to J. All right, let's put all this together. We've got E 1.6 times 10 to the minus 19 coulombs times V 1 times 10 to the 7 meters per second times square root of 2 over 2 times 0.50 teslas times our direction j hat. So the magnetic force on our proton moving as shown is 5.66 times 10 to the minus 13 newtons in the j direction. Now, if you wanted to, for extra practice, you might do this one, finding the magnitude and then using your right-hand rule for direction. We'll go on to the next slide now to do part B. For part B now, we'll solve with magnitude and direction. The magnitude of the magnetic force is the magnitude of the charge times the magnitude of the velocity times the magnitude of the magnetic field times the sine of the angle between the magnetic field and the velocity vector. In our picture, V is all in the negative y direction, B is all in the plus x direction. The angle between those two vectors is 90 degrees because they're perpendicular. Let's go ahead and put our numbers in. Q is the charge on the proton, 1.6 times 10 to the minus 19 coulombs. E is the magnitude of the speed, 1 times 10 to the 7 meters per second. B is the magnitude of the magnetic field, 0.5 teslas. And we're multiplying that by the sine of 90 degrees. All that through the calculator gives us 8 times 10 to the minus 13 newtons. To get our direction, we do the right-hand rule. Your thumb goes with your velocity, so it should be pointing right at your face. Your B should be pointing to the right, and then your extended middle finger should be showing that it points straight up, so it's in the K direction. So then FB, our magnetic force, is 8 times 10 to the minus 13 newtons K hat. And then if you wanted a little bit of extra homework to do, you could try solving this by doing the cross product rather than magnitude and direction. Let's get through a problem now that's got some real meat to it. An electron in a cathode ray tube is accelerated through a potential difference of 10 kilovolts, and it passes through a magnetic field. What's the magnetic field if the deflection is 10 degrees? So what happens is our electron starts here at the 10-volt plate, it moves forward, and it accelerates towards the 10 kilovolt plate until it gets right here. So at this point it's at rest, at this point it's moving very fast, and it has some initial velocity that we could call V0. So it's got some initial velocity right here. That initial velocity is horizontal. As it emerges from the path, it's got a new velocity, and that new velocity is 10 degrees relative to the original velocity. Okay, so the velocity changes. That means there was an acceleration. If we look at what happens within the field itself, when our charge is moving in a magnetic field, it experiences a magnetic force. If we can think about the force and we can think about those velocities, we should be able to figure out the field. Okay, let's get started with the first part, which is when the electron travels between those two plates. It starts at a place with zero potential, so I'm just going to redraw that down here. So the initial potential is 0 volts. Got our electron right here. It's initially at rest and it begins to move until it gets to this place with a potential of 10 kilovolts. So our final potential is 10 kilovolts or 10,000 volts. When the electron gets over here, this is where it's moving. We'll apply conservation of energy. Final energy equals initial energy plus work done by any non-conservative forces. We don't have any non-conservative forces, so that term is 0. Our final energy is kinetic plus potential. Our initial energy is kinetic plus potential. Let's see which of those two terms are 0, or why don't we put it in terms of potential first? So potential energy is charge times potential. Let's see which terms are 0. Well, initially the electron is at rest, so Ki is 1/2 times m times 0 squared equals 0. And our initial potential is also 0, so UEI equals 0. So these two guys are 0. That simplifies things for us a bit. What about our final terms? Well, our final kinetic energy is 1/2 times the mass of the electron times the final speed squared. I'm just going to call that V. And our final potential is our 10 kilovolts. Okay, let's get these things in our equation now. And we remember, of course, really important, the charge on the electron is minus the fundamental charge. So 1/2 times the mass of the electron times the speed as it goes through that 10 kilovolt plate squared minus E times our 10 kilovolts equals 0. That means that the speed as the electron passes through that 10 kilovolt plate is E times VF over 1/2 times M. We take the square root, put our numbers in here. Notice that I'm not dropping a negative sign. The charge is minus E. That term becomes positive when I bring it to the other side. 1.6 times 10 to the minus 19 coulombs times 10,000 volts divided by 1/2 times 9.11 times 10 to the minus 31 kilograms. Take the square root of everything, and that speed turns out to be 5.93 times 10 to the 7 meters per second. And it's going straight across. So now we know the speed when it enters the magnetic field. Let's see what happens to it once it's in the magnetic field. Okay, so now we know the speed of our electron as it enters the magnetic field. We found that out in the previous part. Now we have an electron, a charged particle, moving in a magnetic field. We know it's going to experience a magnetic force. So let's see if we can sort out what that force is going to be. So here's just another sketch of what's happening. There's our magnetic field. Here's our electron moving with speed v in the magnetic field. We can apply our right-hand rule to find the direction of the magnetic force. We put our thumb to the right. Magnetic field is into the page. That's our index finger. We should notice that our middle finger points up. That would be the direction of the magnetic force on a positive charge. But we have to flip that because an electron, of course, is a negative charge. Our magnetic force points down. That matches the setup of the problem that says that the electron deflected downwards. Let's next write our equation for magnetic force. FB equals QV cross B. Our charge Q is minus the fundamental charge. Our velocity has got a magnitude. I'm just going to stick with symbols for right now. Magnitude we'll call V, and it points to the right. And then that's going to be crossed with the magnetic field. So our charge Q is equal to minus E. Velocity has a magnitude of V, 5.93 times 10 to the 7 meters per second to the right. Our magnetic field vector, that one's a little bit different. We don't know what the field strength is, so we'll give the strength the symbol of V. Magnetic field points into the page, so I'm going to take positive X to the right, positive Y up. That makes positive Z out of the page. B points into the page. That's minus B K hat. Okay, so now I've got something to put in for my B vector. I've got a minus and a minus. They multiply to give me a positive. Put all my vector stuff at the end, all my constants at the front. I cross J, or I cross K, sorry. I cross K gives us negative K. Oh my goodness, my words are getting scrambled. I cross K gives us negative J hat. Okay, that backs up what our right-hand rule told us. Now we can stick with symbols or put in some numbers. I think I'll go ahead and put in numbers. So minus 1.6 times 10 to the minus 19 coulombs times 5.93 times 10 to the 7 meters per second times the magnitude of the field B, J hat. Multiply our numbers together, we get minus 9.48 times 10 to the minus 12 B, J hat. So what we found right now is an expression for the magnetic force as it depends on the magnetic field. This is not quite enough to solve the problem because we don't know the magnetic force. However, we know something about the velocity. It deflected down by 10 degrees. That tells us something about the final velocity compared to the initial velocity, tells us about the change. That tells us about the acceleration, which will relate to the force. Okay, let's carry on and let's think about that final velocity some more. So the electron started at a place where it had a potential of 0 volts. It moved to a 10 kilovolt line because it was accelerated through that potential difference. It entered with an initial velocity that we found. So that line of the initial velocity v would go straight all the way through. So that's just the line of the original velocity. But it didn't travel within the original, it didn't stay with the original velocity because it was in a magnetic field that pointed into the page. Because it was in a magnetic field that pointed in the page, it deflected downwards. So it actually traveled a path that looked like this. Now I exaggerated in my picture just to make it easier to see. So that's the actual path. So that means that this is the final velocity. It's deflected down compared to the original velocity. This final velocity has components. It's got an x component, which is to the right, VFX. What you might notice here is that VFX is parallel to the original velocity. The original velocity was horizontal. The x component of the final velocity is horizontal. They're parallel. The y component of the final velocity points down. And the last thing we can do on this picture is we can label our angle. That angle theta is 10 degrees because the problem tells us it's 10 degrees. Let's see what we can figure out about those final components of velocity. The final x component of velocity is the same as the initial x component of velocity. The magnetic force points straight down, so the acceleration is straight down, so the x component of velocity doesn't change, only the y component. So that's 5.93 times 10 to the 7 meters per second. Okay, what about the y component of final velocity? That's the original y component of velocity plus ay times t. What do we know about each of those terms? Well, the initial y component of velocity is 0 because it's originally horizontal. Our acceleration, which is all in the y direction, points down, so it's negative. And acceleration is force over mass. That just comes from Newton's second law that says F equals ma. We said that our magnetic force was minus 9.48 times 10 to the minus 12 times the strength of the magnetic field. We had to leave it in terms of B because we didn't know B. That's divided by the mass, which is the mass of an electron, 9.11 times 10 to the minus 31 kilograms. Do that division and what we get is minus 1.04 times 10 to the 19 times the strength of the magnetic field B. Okay, we've got something to plug in for AY. Can we figure out something to plug in for T? Well, let's think back about the x component of velocity. The x component of velocity is distance over time, and we actually know the distance. It's 2 centimeters wide. So the time is the distance divided by the x component of velocity. So 0.020 meters divided by 5.93 times 10 to the 7 meters per second. That tells us that that electron was in that magnetic field for 3.37 times 10 to the minus 10 seconds. So it didn't take very long to travel 2 centimeters, but that makes sense because it's going pretty fast. Now we've got something to pop in for our time as well. Our VFY is 0 plus minus 1.04 times 10 to the 19 times the strength of the magnetic field times 3.37 times 10 to the minus 10 seconds. That gives us that our y component of final velocity is minus 3.51 times 10 to the 9 times the strength of the magnetic field. Okay, what you might notice here is that we know the x component of final velocity, we know a lot about the y component, and we know that the angle between our components is 10 degrees. We could use a trigonometry function to put those things together. Now let's finish up our problem with some trigonometry. Let's look at our diagram and see that tan of our angle, theta, is the opposite, which is the y component of the velocity, divided by the hypotenuse, which is the x component. And I suppose we'll use magnitudes of those there to be more rigorous. So tan of 10 degrees is equal to the magnitude of Vy, which is 3.51 times 10 to the 9 times the strength of the field, divided by the magnitude of Vx, which is 5.93 times 10 to the 7. You can do your algebra there, and you should find that your magnetic field is 2.98 times 10 to the minus 3 teslas, or 2.98 milliteslas. Let's do another example now. We have an electron moving parallel to a long straight wire with a speed of 0.1 c. The electron is 1 centimeter from the wire. So I'm going to put my electron right here, right up on top of the wire, distance r, which is 1 centimeter. I'm going to say my electron is moving this way and the speed is 0.1 times the speed of light. My r is equal to 1 centimeter, 0.01 meters. Okay, at t equals 0, the wire is attached to a source of potential which produces a 15 amp current in the wire in the same direction as the electron motion. So I attach a couple of wires, hook it up to a battery. When that happens, I get a current flow in my wire, which is going to flow the same direction as the electron motion. And I know that the size of that current is 15 amps. Okay, I've got my current and my distance. Find the force on the electron. Well, I'm going to need to use my equation for magnetic force, FB equals QV cross B. The Q and V parts are pretty easy. What about the B? Well, what makes the B? We have a wire and we put current through it. So that means we have a current carrying wire, and we know current carrying wires make magnetic fields. The size of that magnetic field is mu naught I over 2 pi r. So there's a calculation we can do. 4 pi times 10 to the minus 7 Tesla meters over amps times 15 amps divided by 2 pi times 0.01 meters gives us a magnetic field strength of 3 times 10 to the minus 4 Teslas. But the direction of the magnetic field also matters. We're going to need to use our right-hand rule to find the direction of the magnetic field. So now that we have the magnitude, we also need the direction. Let's find the magnetic field around that wire because we'd like to know the direction of the field at the point where the electron is. So let's say this is our wire, it's carrying current this way. We know that the magnetic field makes big circles around the wire, so it looks something like this. Let's try and get the direction. I'm going to turn side on because these videos with the whole left-right business is kind of weird. So the current goes with the wire this way. So you make a circle with your fingers to reflect the direction of the magnetic field. So your fingers come around this way. At the top of the wire, that's where the electron is. See that my fingers are pointing straight towards me. So the direction of the magnetic field at the top of the wire is out of the page towards me. Let's put that in our picture now. We'll put in our coordinate system, plus x, plus y, plus z. If the direction of the magnetic field is out of the page this direction, that would be a plus k hat direction. So there's our magnetic field vector. Now we'll go back to our force equation and we'll calculate our magnetic force and think about the motion. Let's put everything we know now into our equation for magnetic force. So we've got our charge, which is minus the fundamental charge, minus 1.6 times 10 to the minus 19 coulombs, times our velocity. Our velocity is 0.1 c, so that's 0.1 times 3 times 10 to the 8 meters per second. The velocity is to the right, that's the x direction. Times our magnetic field, which we found was 3 times 10 to the minus 4 Teslas in the k direction. And I dropped my cross there between V and B, so I'm just going to pop it in right up there. I can bring my I and k to the end. I multiply out all my numbers, and I get minus 1.44 times 10 to the minus 15. That's in newtons, times I cross k. I cross k is equal to minus j, so the minuses will cancel. I'm left with 1.44 times 10 to the minus 15 newtons j hat. The magnetic force is going to point straight up. That matches what we would get if we applied our right-hand rule as well. So there's our magnetic force on our electron. If we want to think about what happens to it, so what is the motion? We have our electron. It's got an initial velocity to the right. It experiences a force that points up. So what's going to happen to it? It's going to drift upwards. So its path will be something like this. So it has a constant Vx, because there are no forces in the x direction, but a changing Vy. An exact description of the motion would be a little bit complicated because the force depends on the magnetic field, and the magnetic field depends on your distance from the wire. Your distance from the wire changes, so the force changes, so the acceleration changes, so that Vy would change over time. But it would certainly deflect upwards over time.